Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is advanced modeling features in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer located in Philadelphia, Pennsylvania. My colleague Wieland Gotzer will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel seemed to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, this is the second presentation of a three-part webinar series. So last month I presented the introduction webinar. So this was really geared at brand new users within our program RFEM. So if you did miss that presentation, certainly refer to our YouTube channel and our website to view a recording of that. So we're building on that presentation today to show the advanced features in the program that make RFEM maybe a little bit more competitive than possibly the software that you're using now. For example, we will address model instabilities utilizing one of our add-on modules, Stability. I also want to discuss the use of line releases, which define the connection between beams and surfaces. We'll also take a look at FEA singularities and how we can overcome these with the use of average regions. And finally, we'll move into an FEA connection design. And with this, we want to take advantage of the nonlinear material modeling options within the program with a plastic stress analysis. And for this, we'll be utilizing the add-on module RFMAT-NL. So we will go ahead and get into the main program RFEM here. So again, within the first webinar last month, I really had modeled this particular building from scratch. So certainly refer to that if you're interested in the modeling procedure, the loading, and the analysis. We also touched on some of the design modules. But for today, we're going to start with this model already constructed within the program RFEM. And for the most part, the model is identical to what we saw with webinar 1. It's a two-story steel and concrete structure. There's a few changes that I made just to adapt to the webinar today. But the first topic of discussion are instabilities. And instabilities are not unique to our program RFEM, but realistically they can occur in any finite element analysis program. And it can be a pretty frustrating process because it may be difficult to determine what is the cause of the instability. So my hope is today is to show you how we can overcome these instabilities with a few additional tools within our program RFEM. So what I'm going to do is to jump to our load combination 2 that we created in the previous presentation. Now, load combination 2 includes only dead load and live load. So if we take a look at that applied to the structure, we can see those gravity loads here. And I want to run my analysis within our main program RFEM here. So when I click OK, we're immediately presented with an error message here. And if we go on to read this error message, it says the stiffness matrix is singular, the model is unstable. The instability is found in FE mesh node number 143. So if we drag this dialog box over, we can actually see where the problem may be occurring. Now, this big red arrow is pointing to FE mesh node 143, and oftentimes this is helpful in determining where our instability is occurring, but not always is it exactly at that FE mesh point. But if we continue on reading, we try to give you additional information here to troubleshoot where exactly the problem might lie. The specified load is greater than the critical load. It is possible to calculate the critical load factors and buckling in the add-on module RF stability. So this immediately flags me that this probably isn't a modeling issue, but has more to do with the stability of the structure. And maybe the critical load is being exceeded for one of my members. Well, instabilities can be caused by modeling errors, though, as we know, maybe unconnected members, nodes, lines. Perhaps we have defined support conditions with too many release degrees of freedom. So, in order to troubleshoot instabilities, this is the process that I would take. Number one, I would jump into the load combinations dialog box. And here we can see load combination 2, our 1.2 dead plus 1.6 live. Under the calculation parameters, load combinations are always run according to a second order analysis by default, accounting for big P delta and little P delta effects. Well, I'm going to change this to a geometrically linear analysis. So it's a linear analysis. Our stiffness matrix is going to remain constant for every iteration. Now, the reason why I'm doing this is because I want to rerun this load combination as a linear analysis. If there were any modeling issues, then this load combination would not solve even as a linear analysis. But we can see that the model actually solves just fine when we change it to a linear analysis. So this probably tells me that there's not a modeling issue of members being unconnected, but rather it truly does have to do with the stability of the structure. So what we can take advantage of is one of our add-on modules, RF Stability. And as we covered in webinar 1, all of our add-on modules are listed over here in the Project Navigator, and I can launch RF Stability. So as an add-on module, it's just a simple dialog box that pops up within our main program here. Now, we typically associate structural failure with yielding or maybe deflection considerations. And often buckling is ignored, but it still poses a dangerous mode of failure. And there could be software programs out there that really don't allude to if buckling is an issue within your structure. But you can see within the main program RFEM, we give you some insight that, okay, maybe stability does need to be checked out. Well, the advantage of RF stability is that this will run an eigenvalue analysis to determine the critical load factors and the buckling modes. And essentially, we can evaluate the stability of our structure. So the lowest number of eigenvalues is set to 4 here by default. And quite realistically, a low number of eigenvalues will give you a sense of what could be the issue within your model. When you're getting into very high eigenvalues, the likelihood of that particular buckling mode occurring is quite slim. So by default, we can go ahead and leave this as 4 eigenvalues. Now we want to import in here the axial forces from load combination 2. So remember, this is my linear analysis because I changed it, and we'll import in those axial forces. A couple things to note here. You do need to import in a load case or combination that does run back in RFEM. So if I tried to import the original load combination 2 as second order effects, I would get an error in RF stability because it can't solve for these eigenvalues with a load case or combination that doesn't solve within RFEM. We also want to choose a load case or combination with the highest axial forces here to evaluate the stability of our structure. We certainly want to take into account the worst case scenario, which means the highest axial forces to cause buckling within our structure. So that's why I'm choosing one of these gravity loads. Now, there is the option down here with this checkbox to calculate the eigenvector for an unstable model. So the cause of an instability can be checked graphically. So this could be used in the event that we just absolutely could not get the model to solve with any load case or load combination back in RFEM. You'll notice that when I check this box, the load case and combination is grayed out, the eigenvalues are grayed out, and this is simply because this will allow us to run a load independent eigenvalue analysis, and maybe we can determine where the modeling error takes place. Maybe we have a member flying off somewhere because we forgot to connect it. So this can be extremely beneficial, not just for buckling and the stability of our structure, but to determine modeling errors. But for today, we are moving forward with the stability, so we'll uncheck this option. Now, the stability analysis includes a linear buckling analysis by default. Those are the settings over here on the right. We do have the ability to run a nonlinear analysis. So if we have geometric nonlinearities, material nonlinearities, you can check the stability of the structure according to this nonlinear analysis. Just keep in mind it will take a little bit longer to solve here as well. So what we can do is to run the calculation of the eigenvalue analysis, and the program will determine the first 4 buckling modes. And eventually we'll be presented our results here within the add-on module. So the first table here is the critical load factors. And you'll notice that I have 4 results here for my 4 different eigenvalues. And all have about the same critical load factor of 0.58. Well, if I drag this down, I actually can see the different buckling mode shapes of my structure. Now, all critical load factors are the same because it has to deal with these 2 columns here buckling in any direction. So what exactly is the critical load factor? This is the factor that you can multiply the applied loads from load combination 2 by before you see buckling behavior shown in the background here. So anything below 1.0 is a big problem. This means that the model can only take on 58% of those loads from load combination 2 before these slender columns are going to buckle. You'll also notice on the second tab here, pretty useful, that we actually show the effective lengths and the effective length factors for all members based on these 4 different eigenvalues. And you can kind of see in the background, the model will highlight the member that we're currently looking at in the table. Now, how this can also be beneficial is we can export the effective length and effective length factors to our other add-on modules such as RF Steel AISC if we're designing per the effective length method, for example. So jumping back to the critical load factors, I can go back to my results within RFM. So I'm still within this RF stability add-on module. I'm just viewing the different buckling mode shapes here. So again, we're looking at the buckling of these columns, and the critical load factor is essentially the same for all of them because the program doesn't necessarily know in which direction it will buckle because these are square columns. So you have a couple options with this. Number one, you can decrease the loads that are being applied, but most likely that's not an option. So number 2 is just to increase the size of the members. If we take a look, I mean, obviously these middle columns here are pretty slender. So maybe we made a modeling error and we'd actually prefer for these to be 12-inch by 12-inch columns. So what I can do is just to select these 6 by 6 columns within my cross sections drop down box here, and I can double click on the members. I can use my drop-down box to choose the 12 by 12, which I've already defined in the model with my exterior columns. I can clear my results, and now you can see that the model looks quite a bit better. So to ensure that our model solves okay, we go back to our load combinations. And we take a look at load combination 2 here. We change it back to second order analysis. We click OK, and we're going to rerun the calculation just to make sure that everything solves. And sure enough, we should be presented here with our deflection results, and we are, so everything is fine once we increase the size of those members. All right, so hopefully that gives you some insight on how we can address instabilities within the program. The next thing to move on to is a feature called line releases. So previously in webinar 1, if you remember, we defined these members sitting below our surface as rib members. And if I double click on one of these rib members, you can see the member type was set to rib. Now the benefit of a rib is obviously we're going to drop the member down below the thickness of the surface, so we're going to apply an automatic eccentricity. But we also applied an effective width on either side of the slab of 3 feet. So this is beneficial because now the internal forces, once we run the analysis, will consider this effective width on either side of the beam. But also we can design these T-beams in our concrete design modules to consider for the reinforcement as well. But what if we have the scenario here that these are some type of prefabricated downstand beams, meaning that these beams were precast and they were brought on site, and this slab is actually just sitting on these beam members. I don't want the connection, the fully fixed connection, to be defined along the member length. So what I can do here is to select all of my members by type under my Views tab, and I can choose my rib members only. So now you'll notice everything else is grayed out within the model. I can highlight all of my rib members, double click, and the first thing we want to do is to change these to just typical beam members. But you'll notice once I click OK, it asks me to clear my results once again. These beam members are placed at the center line of the surface. So I've now lost that eccentricity from my rib member. But in reality, I still want them to be dropped below the surface of the slab. So once again, I can highlight all of these members. I can double click, and we can utilize this second tab here to set a member eccentricity. Well, I create a new eccentricity type, and in reality, I could calculate half the depth of my beam, add this to half the thickness of the slab, and to manually type in the eccentricity at the member start and member end. But it's much more effective to use some of these automated options within the program. So the program can actually offset our beam from a set object within the model. I want to take the top point of my beam member and I'm going to offset it from a particular surface. And what I can do is I can graphically select the surface by canceling out my visibility mode. I can choose either the top or bottom surface, and I want to select the underside of that surface. I click OK, and now you can see that eccentricity is considered now. But we still have this fully rigid connection between the beam and the slab that we would like to take care of. Under the Data tab, this is where we want to utilize what's called line releases. So in the Project Navigator, I can right-click on line release types to create new type. And you'll see here I have 4 degrees of freedom that relate to the local axes of the line. So the X, Y, and Z axes here are not the local axes of the beam, and they're not the local axes of the surface, but every line element actually has its own local axes as well. So here is where we can completely release the moment about the local x-axis of the line. So this is along the member length to for this prefabricated beam just sitting on the slab. Maybe we'd also like to release the translation along the length of the beam, which would be in the local x direction of the line. And lastly, in terms of the vertical considerations, maybe when this beam has downward deflection, I would like it to fully bear on this beam. In the event that we have any upward deflection of this beam, then I want that connection to be completely broken. And how we can do this is what's called a nonlinearity. So we apply this in the vertical direction here, and we have the option to choose fixed if positive Z. So in other words, when I have downward deflection, I'll have full force transmission between the two elements. If I have uplift, then we will not see any force transmission at all between the two elements. So I can click OK, and now you'll notice under the line release types, I've defined this new type. I can right-click under line release to assign a new line release graphically. The line release type, we just select the type that I just created in the previous dialog box. I want to first select my bottom slab here, surface number 6. And then once I click OK, the program allows me to choose the lines that I'd like to apply this to. So you'll notice I'm choosing the lines that are shared between both the beam member and the surface. I right-click twice to repeat the last command. I now choose the top surface here. And once I click OK, the program will allow me to choose the top 2 lines. Now you'll notice the line release symbol is indicated by this blue color here. It looks like a box along the full member length. So what I'd like to do then is to run load combination 2 once again, and keep in mind this will take a split second longer than what we just saw because we've now introduced a nonlinearity within the program in terms of the uplift versus the downward deflection and the force transmission between the beam and the slab. Eventually, once this is done solving, we will be presented with our results within RFEM. So initially we're looking at the deformation here. And I'm jumping to my results tab within RFEM. And what I'd like to point out, which we had previously discussed in webinar 1, is that we can view the internal forces here of our members based on the analysis from load combination 2. And I'm going to focus in on this rear beam here, and I'll create a visibility by the selected objects. So we can view the internal forces such as the axial loads, we can view the shear, for example, but I want to focus on the torsion forces. You can now see that after I applied that line release, the torsion is essentially 0 along the full member length. We just have a small torsion of 0.043 at either end where that beam reconnects back into that column. So I think we can effectively say that our line release was applied. Now we can compare this to the previous rib member. So you'll notice here that with the line release, I had just shown you that the torsion is 0.043 kip feet, so essentially 0 along the member length. If we compare that to without the line release, when we previously had a rib member defined, we're going to see a much higher torsion of 122.068 kip feet. So significant difference here when we're looking at the application of line releases. All right, so that sums up the tool for line releases, and we want to continue moving on within the presentation. The next thing to take a look at is I'll turn back on my results, and instead of taking a look at the members, let's look at our surface results. So remember, this is still load combination 2 here, and we're currently looking at the internal forces. You can see we have MX forces, MY forces, we can take a look at shear, and these are all available to us within the model with these nice contours. But sometimes with surfaces, we want to take advantage of what's called section cut. So a section cut, exactly as it sounds, it will take a cut directly through the surface so that we can see the internal forces occurring at that exact location. So how I create a section cut is to turn off first the results here. I'm going to turn on my grid, and I want the section cut to be along the center column and beam line here. So I'm going to move my drawing grid right at the top of that column. Now you'll notice, you can see here the drawing grid is located at that position. We're going to use that to our advantage when we're drawing this section cut. So I use my quick tool up top to create section numerically. And we need to first give it a section name. We'll just call this one 1. We do want to define the 2 points that define the section ends, and we can do this graphically. And again, utilizing this drawing grid is helpful so that we can just snap to the 2 points at that column location. The program will automatically populate the node coordinates. We want the projection direction to be in the global Z direction, so the upward direction. We also can show our results in the global Z direction, and we want it applicable only for our top surface number 5 here. So when I click OK, the program automatically brings us into what's called a results diagram. With the results diagram, we can turn on and off forces here along the length as well as deflections. You can see here I'm going to turn on MX and MY forces. And I think it's very clear where our column is framing into that slab because we're getting higher peak forces here. Keep this in mind because this is actually something that we'll revisit a little bit later on. But essentially this is nice. It's giving us that section cut right through the surface. Now if I exit out of this results diagram, I'm going to go back to my results for load combination 2. We can actually see this section cut drawn within our model. So right now I'm looking at MX forces for my surface. I even have the ability here to turn off my ISO bands so that I'm only viewing that section cut across the top surface. Now, even more so, we can take these sections and I can just highlight it graphically. I can use my move copy tool here to make one copy, and I'm going to offset it from my front column to my rear column line. I click OK, and now you can see I have a new section cut generated at the rear column, which reflects the internal MX forces of my surface. So we don't even necessarily need to rerun our calculation, but we can create multiple section cuts. We can even turn them on or off here within our results diagram if we're interested in seeing those. Now, section cuts are extremely beneficial if we wanted to show those within the model here, but sometimes we're just interested in a general overview of what's going on with the internal forces, but nothing permanent that we can display within the model. So I want to suggest another tool that we have called our clipping plane. And we can find this under Insert, Clipping plane. Now, clipping plane is exactly as it sounds. It essentially makes a clipping plane right through our structure here. We can invert the clipping plane, and what we can also do is display the results here. So I'm going to turn off my previous sections that I just created, and you'll notice that I'm essentially getting a section cut through this clipping plane as well. So with the clipping plane, we can decide the step distance. So maybe I set this to 6 inches. Then we can toggle on or up and down with the tool, the offset tool here, to actually show the internal forces along these particular surfaces. Under the Display tab, you'll see here the sections tree. We can turn on all values here as well if we're interested in seeing the internal forces, which right now we're currently looking at the MX forces at that particular clipping plane cut. So you can imagine that this is extremely beneficial if we don't want to sit there and create sections at each individual location, but we're just trying to understand what's going on here. You even have the ability to reverse the clipping plane in any one of the directions shown here, or you can even create your own work plane at an angle. Maybe for this, we change our view to MY forces, and then again, we can toggle with this offset tool to view the internal forces at that particular clipping plane location. But keep in mind, the minute that we exit out of this clipping plane, we lose those result diagrams from those temporary sections. So this is why the permanent sections might be a little bit more beneficial, but the clipping plane is nice if we're just interested to see what's going on for a brief moment. Now, clipping planes can also be used for solid elements. This is where they become extremely effective because we can't necessarily see the internal forces and stresses within a solid element, and that clipping plane will slice right through the solid element to show us exactly what's going on. All right, so moving on now, I want to address what's called singularities. And as I had shown you previously with some of these section cuts here, that we have these high peak forces at our columns. And what I want to do is to jump into one of our add-on modules called RF concrete surfaces. So previously in webinar 1, we touched on reinforcement design for concrete members, but we didn't dive into RF concrete surfaces. So this add-on module allows us to perform reinforcement design according to the ACI, the CSA, as well as some other international standards for concrete surfaces. Now, I'm really not going to go into much detail today, just simply for the lack of time, but I do have previous webinars dedicated to only this add-on module that go much more into detail about how we can do reinforcement design. So I'll fly through this today, but I'm doing it for a specific reason. We will want to do design according to the ACI 318 here, and I'm only going to choose, once again, my load combination 2 for my strength limit state. I'm even going to skip serviceability for now. And then we can just simply move down our list here to view the materials, 4,000 PSI concrete. We have only a couple surfaces available to us to design. And under the reinforcement table, so this is going to allow us to specify some reinforcement limitations based on the ACI code or our input values. The first thing to note here is that we want to only design this top surface. So I'm just going to design surface number 5. I can graphically select it here. So quickly jumping through these other tabs, reinforcement ratios, reinforcement layout would include the cover, for example, the longitudinal reinforcement if I had any provided reinforcement. Let's say I know I want to put in here at least number 6 is at 12 inches on center. Well, I can input in that reinforcement and the program will let me know if that's adequate or if we need to add more reinforcement. And the ACI 318 tab, this just has some reinforcement minimums according to the standard. We will use this first checkbox here that we want minimum longitudinal reinforcement for plates. So again, just flying through this only because I want to run a quick calculation of this surface to show you that once we are presented with our results, you'll see here quite a bit of red text, and red text is usually never a good thing in a program. You'll see that we have both the top and bottom reinforcement for this surface shown, but it's actually giving us an error saying it's not designable. And we can see our message down here in the lower left corner. We can also access it with the messages box here. It tells us the allowable compressive stress of the concrete in the strut direction is exceeded. So if I go to the by point design, so this is showing me the reinforcement at every FE mesh point here, you'll notice that at many locations, the reinforcement is actually okay. We are getting top and bottom reinforcement. And I know it's a little bit hard for you guys to see, but there is a big red arrow here showing me exactly where that particular point is. So it looks like there's only a few locations where I'm not getting reinforcement that's designable. So what I'd like to do is to go back to the RF concrete surfaces add-on module here, but I'm viewing my results graphically within RFEM. And maybe I highlight this top surface only here. Everything else will be grayed out so we can kind of understand what is going on. I take a look at my required reinforcement at the top, and you can see it's spanning from the left to right direction indicated by this symbol here. Well, the first thing we'll notice is that we have pretty high reinforcement peaks at this column. Then if we also take a look, this is where we're not getting reinforcement altogether at this sharp 90-degree angle here. And actually, both of these are a result of singularities. And again, singularities are not unique to RFEM. Singularities happen in any finite element program. So it really comes down to, does your software have the tools to let you overcome issues such as this? And if we take a look also, I wanted to show the reinforcement in the additional direction. So this is spanning from top to bottom here, still the same issue. When we look at the bottom reinforcement, it's a little bit better, at least at the column locations, which makes sense, but we still have the issue at this corner. So if we turn off our results here and I take a look at the wireframe view, singularities can occur for a few different reasons. Number one is we have this column framing into my slab element at this tiny little FE mesh point here. And there's actually no load distribution at this location. All forces are occurring at this one single point. So when the program goes to do the reinforcement design, it just sees it's extremely high internal forces at this location, and all it knows is to design the reinforcement accordingly. So what we end up with is entirely too conservative of reinforcement design at these locations. The other issue for singularities and why they can occur is reentrant corners like this. Sharp corners that maybe don't have any type of curvature here. Well, we're going to get a lot of force distribution right here without really distributing it to the other FE mesh elements at this location. And so in reality, we're not going to get design at all, as we saw with the concrete surfaces module. So how to overcome these singularity issues? Well, this is where I want to take advantage of what's called average regions. And under the data tab, we can find average regions here in our list. We can right click to create a new average region. So this tool allows us to select the surface. We'll just select our top surface here, number 5, and we can create an average region as a rectangle, a circle, or an ellipse. So we'll stick with a rectangle with the dimensions of 3 feet by 3 feet. Then I need to choose the location to apply my average region. So I want to choose that node right at the top of my column. Now over here, the program's asking us how we want to average these forces. So essentially, I'm going to average all internal forces in all directions over 3 feet by 3 feet location at the top of that column. So each average region has a local axes U and V, and we're averaging it relative to the local axes of the surface X and Y. Now you also have the ability here to set the result values over the entire region to 0. So if you're completely not interested in what's going on at the top of that column, and rather you'd like to assign the ability to set all values to 0, you can do so with an average region as well. So once we click OK, you'll see here the average region symbol shown right around that column. What we can do is to highlight it, hold down my control key, and to make a copy to that rear column. And the program's smart enough to know that, okay, I'm still applying it to the same surface, I've just moved location. So I'm going to average all of my surfaces, or all of my internal forces of the surface right at that location as well. I can even more take both of these average regions, hold down my control key, and to copy them to the other side as well. So now I've quickly created 4 average regions at all of these column locations. Now we still have the issue up here at this reentrant corner, and we might be wondering, well, okay, how do we deal with the singularity that occurs there? And the answer is also with average regions. So once again, we can right click to create a new average region. This time we do want to apply to surface number 5, but I'm going to create a circular average region with a diameter set at 3 feet. I want to choose my location, which will just be that corner node where the reentrant corner takes place. The program automatically fills the node locations in the X, Y, and Z coordinates. I'm going to average out in all directions. I click OK, and now I can see an average region indicated right there at that corner. Now, in a similar sense, I want to hold down my control key, and I'm going to copy this over to the other side. So what's nice is that if I take a look at load combination 2 here in my results, I don't have to rerun the calculation. The program will simply smooth my results automatically. And you can see that my average regions are available to me here. I can turn them on or off. And you'll see, focusing in on this first average region, when I turn it off, that peak exists. When I turn it on, then we're going to smooth out those internal forces. I can also right-click to view my results diagram here, and you will see that with the result diagram, we can turn on only MX and MY. That again, we're going to smooth out those peaks quite a bit. So that's the application of an average region within the main program. But if we go back to RF concrete surfaces and we launch the add-on module, we take a look at our design, we're still seeing this red text. So the question is, well, why aren't these average regions being applied? And the reason why is because this is a two-step process with average regions between the main program and the add-on modules. We want you to tell us if you want the program to design considering these average regions or not. And we can do so under the General Data tab. If we go under the Details settings, we have the ability here to apply the average internal forces from the average region. So now the program will consider this for the reinforcement design of this surface. Now, this is also true for some of our other add-on modules. Singularities can be an issue with cross-laminated timber design, for example. So in a similar manner, we have the ability to apply average regions for CLT design. Same thing with our surface steel design module. So once we click OK, we need to rerun our quick calculation here. It solves within a split second. And now we're seeing reinforcement design for both the top and the bottom in both directions. We can take a look at our results within the main program here. We'll jump to RF concrete surfaces. We'll view our top reinforcement. Now we're still seeing higher reinforcement at these locations, but maybe it truly is needed. So that's up to you as an engineer to determine if this reinforcement makes a little bit more sense. But certainly now at least we're getting results where previously we were not at all. We can take a look at reinforcement in the oriented in the 90-degree direction on top, as well as our bottom reinforcement. You can see these reentrant corners are not even an issue now when we take a look at our bottom reinforcement. So hopefully this gives you some insight on singularities and exactly how we can use average regions to overcome those. All right, so the last thing to discuss here is so far within webinar 1 and webinar 2, we really have worked on a much more global level. And what I mean by that is we've been designing the entire structure as a whole with these large members and large surfaces. But where RFEM is actually also very powerful is its FEA capabilities on a much more local or smaller scale level. So what I'd like to utilize these powerful features for is for the FEA of a connection design. And I'm going to highlight the steel truss that we created last webinar to create a visibility by the selected objects. I can zoom in here and maybe I right click to turn off the hidden objects in the background. So when it comes to the FEA for a connection, pretty straightforward connections, maybe this isn't so useful, but FEA does come into account when we have very complex connections that we really just can't design with analytical checks from the AISC, for example. We maybe also want to run an FEA when we have extremely large loads on a structure and then we want to move to a plastic analysis and design. So for today, I want to focus on the FEA design of the connection at this single joint here. And I'm going to turn this into wireframe view, and I'll delete this set of members that we previously created. And you'll notice that I have these couple members here. I'm going to hold down my control key to select both of them, right click, and I'm going to reverse the member orientation. So the reason why I did that is I now wanted all members to start at this common node here, which you can see that indicated by the red arrow for each one of these members. So I'm going to highlight all of these members, right click, and under the member option, I have the ability to divide the member by a certain distance. So I can choose this distance here, and I'm going to select 2 feet from the member start. So now when I click OK, all that I have done is broken apart these members into 2 separate segments. Now, if I were to rerun the calculation, the program still treats this as one continuous member. I just simply had broken it apart. And the reason for this is that with every FEA program, we know that members are represented as 1D elements. And this is clear when we're looking at it in wireframe view. These W sections are represented by a single line. So I'm going to take all of these members here, and I'm going to right click. And under the member option, we have the ability to generate surfaces from member. So what I've done here is I've just converted those 1D member elements into 2D surfaces for my flanges as well as my web elements. And what this allows us to do, if I turn this into a rendered view, is that we can transition quite nicely from these 1D member elements into these 2D surfaces. But now all of these 2D surfaces are going to be fully meshed, and we're going to be able to run a stress analysis, for example. That's something that would not be possible with these 1D member elements. We need to convert them to surface elements. So a few things to consider here. Number one is that we obviously need to clean up this geometry a bit. So if I zoom in, all of the members are still connecting at this common node. Well, the first thing I'll do is to delete the center lines indicated by these blue lines because we no longer need them. The other thing is that we have many AutoCAD-like features within the program. So it's actually quite easy to quickly clean up this geometry. So for example, I can select my nodes at my bottom web member here. I can snap to the top chord flange. Same thing for the top flange of my web member here. I'll snap to the point where it meets the bottom flange. And then I want to do the exact same thing on the right hand side for my web member. So I'm just highlighting these nodes and selecting them, and you'll see that the program automatically determines where that snap point is. Now, of course, we need to do the same thing with our vertical web member, and it's quite easy here. What I'm going to do is just to snap this point up to the bottom chord. So you can see within a matter of seconds, we can easily clean up that geometry. Now, the next thing to note is that we have these 1D member elements framing into these 2D surfaces here at this one single FE mesh point. And as we just learned, we're definitely going to get a singularity here. We have all this force acting at this one tiny FE mesh point with no load distribution. So this is actually not where I would recommend applying an average region, but rather we want the force from this 1D member element to be distributed to the entire face of all of these surfaces. Well, we can do so with what's called a rigid surface or rigid plate. We can go up here to our tools and we can choose a new surface, and the shape that we'll choose is a polygon. So the polygon stiffness will be set to rigid. You'll notice that when I choose rigid, my material is grayed out, my thickness is grayed out because this doesn't matter. We're using a very, very high stiffness so that any of those properties really don't matter. And what I'm going to do is I'm just going to snap to these 4 endpoints here to create my rigid surface. Now, once I render this, this will be a little bit more clear. But we need to do this at all locations. Otherwise, we're going to deal with the singularity at every one of these locations where the 1D member element is framing in to the 2D surfaces. So we do so on the right-hand side of our structure, and you can see that I had messed that one up a little bit. No problem. We'll choose polygonal surface. It remembers my settings, and we'll choose the 4 points here. And lastly, we want to do the right side. So once we are done applying these surfaces, let's turn this into a rendered view. And now you can see those bright pink surfaces represent the rigid end plates here for load distribution. Now, the other thing to discuss is our FE mesh. So under the calculate FE mesh settings, which we visited in webinar 1, the global FE mesh is set at foot. Well, that's entirely fine for our larger surfaces that we've been looking at so far for levels 1 and level 2. But when we're looking on a much smaller scale, such as this, 1 foot is entirely too big. Well, the program's actually smart enough when we converted these 1D member elements into 2D surfaces to place what's called an FE mesh refinement on each one of the surfaces. So I turned those back on with the FE mesh refinement symbols, which we can view here. What the program automatically did was refine the mesh at every one of these surfaces to 1 inch. So you can see how this is much more effective for a much smaller scale than 1 foot. Now, if we take a look, we actually can generate the FE mesh, and I want to turn it on under my display tab here. We'll turn it back into wireframe view, and you can see that the program automatically accounts for all of the nodes, the lines, the members. Everything is meshed automatically based on that 1 inch setting that the program has put in there. But yet in the background for our larger surfaces, if we take a look at the hidden objects in the back, we will see that the 1 foot is still being used for these larger surfaces. So this is incredibly beneficial because we we don't want to change the FE mesh for our larger surfaces to 1 inch. This is going to drastically increase our solution time. So we're isolating it to only these surfaces here. Okay, so turning this back into a rendered view, let me go ahead and hide those objects in the background. I'd like to take a look at my dead load case only. And previously in webinar 1, we applied a member load to our top chord here under dead load, which is shown as such. But let's say in the event we're actually doing this connection design here because we want to apply some pretty large axial loads on these web members bearing down on this bottom chord. So what I need to do is to apply some additional nodal loads to this particular connection. And I can do so by, let's go ahead and apply a new nodal load up here in my toolbar. And up pops our dialog box. Now, if I want the load to be along this member, remember I said I wanted a very high axial or normal force on this particular web member. So normally we would think, okay, well, we must have to convert that load into X, Y, and Z components that are compatible with the global axes within RFEM. But we actually have a nice feature here where we can rotate these nodal loads. Within this drop-down box, we can choose a coordinate system, we can choose 2 nodes, maybe the same as a member or same as a line. When we choose same as a member, this allows me to graphically choose a one-dimensional member in the background, so member number 81. Then I can apply my force magnitude, which is pretty high at 70 kips, let's say, for example. I click OK. I'm zooming in here. I apply that nodal load to that rigid plate, and now we can see that nodal load is being applied along the member length in that exact same direction. So very nice that we don't necessarily need to convert those into the global X, Y, and Z components, but we can apply them the same orientation as that web. Now, same concept for our vertical web here, but this time with our nodal load, there is no need to rotate it, but rather we can apply it in the global Z direction of -70 kips. I click OK. I can zoom in here to the top node for that rigid plate, and we can see that nodal load being applied at that location. And finally, we want to do the exact same thing on the right-hand side. So we choose a new nodal load once again, but this time I need to choose the same as member, but I need to edit the member here, which I can graphically choose member number 82. I click OK. I still use -70 kips. I click OK. And so now, oh, sorry, we need to actually apply it to the node here. And now you can see that nodal load is being applied to the right-hand side as well. So these are all under the dead load case. So for the sake of this simple example with our FEA connection design, I'm going to run the analysis here according to dead load only. So what the program will do, we'll go ahead and apply these dead loads shown here, including on this connection, and we are presented with our results. So initially, the program is showing us our internal forces, and we can see MX, MY forces, but probably for this connection design, we're more interested in stresses. So stresses are available to us with the add-on module RF Steel. RF Steel releases all of these different stresses within the add-on module, or within the main program RFEM. The add-on module allows us to also run a stress design. But within the main program RFEM here, to look at all these various stresses, we have normal stresses, principal stresses, shear, pretty much any stress that you can think of. But we probably are most interested in the von Mises stresses. And when I turn on the von Mises stresses, I take a look here at my colored contour panel, and I see my max stress is 73 KSI. Well, that's a problem. When we converted these one-dimensional members into 2D surfaces, these 2D surfaces took on all those properties of those W sections, including the correct thickness for the flanges, the webs, everything else. It also took on the material of steel A992. Well, we all know that steel A992 has a yield strength of 50 KSI. So it's absolutely not possible that any one of these FE elements can experience 73 KSI. But you'll notice that for all of these surfaces, if I double click once again to take a look at this material, again brought over just from those one-dimensional elements, the material model by default is set to isotropic linear elastic. So the program only knows what it's set to. It's just an elastic material. It applies a load. The stresses are what they are, even if the yield strength is being exceeded. So what we would like to do is to create a new material for all of these surfaces. So I access the new material dialog box and I go into my material library here, and I'm using my filters over on the left to filter to steel, to the AISC standard, and here we'll find steel A992 again with the applicable properties. Now nothing has changed here so far. But what I do want to change is the material model. So the add-on module RFMatNL releases these nonlinear material models in RFEM. So RFMatNL is not really a module that you can open up with a dialog box. It just simply allows you to consider the rest of these nonlinear material models. And for today, we want to utilize the isotropic plastic 2D, 3D. So this is for surfaces and for solid elements. Now immediately this dialog box pops up that shows us our yield strength, which was taken from steel A992 as 50 KSI. So once we have determined that the yield strength is set properly here, we can click OK. We can click OK once again. So now you'll notice it's asking me to clear my results. If we jump to the data tab here, and now we can take a look at our materials defined, steel A992, which is running a linear elastic material, is still being used for all the rest of these members within the model. I know it's a little bit difficult for you guys to see, but all these members are currently highlighted in red. But if I take a look at my third material I just created, isotropic plastic 2D, 3D, this is being used by only my surface elements at this connection. So now what we can do is to rerun this dead load case. So I'm still applying those high axial forces within my web members. Now this does take a split second longer because we've introduced a nonlinear material model. The program must determine which elements are fully yielding and which are not. So eventually we will be once again presented with our results within RFEM here. And the program will jump us to the von Mises stresses once again, and I can zoom in here and I take a look at my colored panel and I see my stresses as 66 KSI. Well, this is still a problem. Why am I seeing stresses higher than 50 KSI if 50 KSI was set at my yield strength? And there's actually a good reason for this. So currently right now, the program is smoothing together all these values at every FE mesh point to make a nice contour for us. So this is great when we're graphically viewing this. It creates a nice picture for our printout report as well, but it can often skew what our actual results are here just due to that smoothing algorithm. Under the Display tab within RFEM, we can navigate down here to our results tree, and we expand surfaces, and we can also expand here the distribution of internal forces and stresses. The default is continuous within surface, so this will apply that smoothing algorithm. Instead, we're going to change this to constant on element. So now each individual FE mesh element has its own color, and now we're not seeing any stresses higher than 50 KSI, which is exactly what we'd expect with a plastic analysis. The minute that any one of these FE elements reaches the 50 KSI, it yields and the load is further distributed to the adjacent elements, and it continues to do so until the load is fully distributed. What the program also allows us to do on top of viewing the von Mises stresses is we will see a criteria tree here in our results. We can actually take a look at the elements which have fully yielded, or that are very, very close to yielding. So we can turn this on and now we can see the individual FE elements that are really a problem under these high applied loads. We can also view the design ratio. So what this is telling us is this is the demand stress, our von Mises stress, over the yield stress of 50 KSI, and it will output a design ratio here in terms of these colored contours. So this gives us much more insight into what's exactly going on with a nonlinear plastic analysis. Okay, so we will go ahead and conclude today's webinar. As always, that's quite a bit of information, but you can go to our website at dlubal.com to learn more about both the main program RFEM as well as the add-on modules. We also have our web shop available, so we display all of our pricing for the program and these add-on modules directly within the web shop if you're interested to look at those. I always encourage everyone to follow us on our social media sites. You heard me mention our YouTube channel, for example, that has previously recorded webinars. Some of our other channels, Facebook, Instagram, LinkedIn, will go ahead and announce events and conferences that might be taking place, new technical articles, frequently asked questions, and such. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office at info-us@dlubal.com. And our phone number here is 267-702-2815. So we will have many more upcoming webinars. Webinar 3, a part of this 3-part webinar series, will take place on August 20th. The topic for that is BIM integration and RFEM. So if you haven't already registered, you can go to our website at dlubal.com under support and learning and webinars. As most of you know too, I send out a couple reminder emails before these webinars will take place, so feel free to register through the email reminders as well. Many of you are wanting PDH certificates for today, and that's great. These will automatically be emailed to all participants. So if you were available for today's presentation, and we do require that you were here for the full presentation because it is a requirement of the states that we have the ability to provide PDH credit for, then this will be automatically emailed to you within the next 24 hours. If there was anybody who watched today's webinar that didn't specifically register under their own name and their own email, for example, maybe you had several colleagues watch with you or you watch under a colleague's registration information, then you will need to request a PDH at info-us@dlubal.com. So again, if you yourself did not register under your own email address and your own name, please request a PDH at info-us@dlubal, dlubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.